And I think what you'll see is that this is kind of you could call it mindless, in the sense that once you know the recipe, you kind of immediately know what questions you have to ask yourself. There's still thinking required. You have to answer the questions, but it's great to know what questions you have to ask yourself to solve a problem. So we have to ask ourselves, what's hidden? Well, clearly, where the prize is located is hidden, and we can choose some nomenclature for that. We have 3 possible hidden states, A, B, C, and as I said before, I will try to be consistent about using Greek letters for hidden variables, and I strongly recommend the same practice to you. It's wonderful when you look at an expression to be able to just know at a glance what are the hidden variables versus the observables. The obvious rule for observables is I just use regular Latin or English letters to represent observable variables. Okay? Any questions on that? Okay, we jump to our next question of what we should use for our observable variable. Clearly, we want to be able to refer to which door was observed to be empty, and we can at the same time also talk about what we're going to use for our prior probability. Well, in this particular problem, it's dead easy. It's pretty much given to us. He said uniform probabilities. Okay, so the prior probabilities are equal. Questions? Okay, so the core to inference, the step that really matters most, is finding the connection between our hidden variable and our observable. In this particular case, that connection came from the insight that, if the prize is actually hidden behind door B, then B minus is clearly impossible, 0 probability. And then that clearly is going to give us some bias. So then all the probability has to go to probability C minus given delta equal D. And A was the door that we picked. Monty doesn't have any choice. He's going to have to open door C in order to show us an empty door that wasn't the door that we picked. Okay? So in general, I strongly recommend that you think of these likelihoods as a model. In other words, these are things that we just make up to represent some situation that we think is possible, right? It's to a certain extent what we mean when we talk about hidden variables. We are kind of making up a model for how the world works. For example, if I think that sequencing errors in a sequencing machine happen completely randomly, then I expect them to follow a binomial distribution with some underlying error probability that I can measure directly from my data. I just want to make the hopefully obvious point: the fact that I can make up a model like that doesn't mean it's right. Right? I mean, there might be something about the machine that's badly engineered that causes strong biases in its sequencing error patterns. Like maybe it always makes mistakes at the beginning of the read and much less in later parts of the read, or what have you. Okay, so the key insight with Bayes' law is that we are not required to be sure that our models are right. Why? Because we can calculate the probability of the observations under each one of the different models that we think are possible or plausible, easy enough to compute. And the Bayes' law will tell us whether we have data that clearly match one of our models, giving it strong posterior probability, or whether we have basically uncertainty that these observations are about equally likely under your different models, so there's no way to know which of your models is right. the great thing about Bayesian inference is that it's very naturally adept at taking into account whatever levels of uncertainty we are able to write down. When I say write down, what I mean is write a likelihood model. You can write a likelihood model that you can compute. You can compute, posterior odds ratios, if you will, that say how sure am I that it's more likely to be this model than that model. Okay? Questions?
In this case, delta equal to A, delta equal to B, and delta equal to C are three different models, right?
Right. You could think of those as being three different models of how Monty's going to behave, and we expect him to behave differently under those three different scenarios. We could make up additional models even if we wanted to. Maybe we have a model where Monty's drunk, and he just forgets where the prize is with some probability or something like that, right? We could add more models to this, and maybe if Monty really was a heavy drinker, it might actually improve the accuracy of our predictions. Other questions? Okay. So the last ingredient that we need for Bayes' law is, how are we going to get the denominator? I mean, sometimes if you just ask the question in this form, what's the probability of the observation? It may seem kind of mysterious. Like, well, how am I supposed to figure out how likely it is that I'm going to observe the particular value when I don't even know what's going on? The classic answer to this is that we basically just treat this as a normalization. In other words, we take our numerator and we sum it in our denominator over all possible models. If we are truly able to enumerate and compute all possible models, then this becomes exact. If not, it becomes an approximation. And how good or how terrible of an approximation is a whole other question that we may get into later in the course. But the bottom line is we typically compute the denominator of Bayes' law through summation. Okay? Any questions about that? You basically think of it as normalization. You take what's in your numerator, put it in your denominator, you sum over all possible values of your hidden variable. Okay, so with all that in hand, it's just a matter of writing down Bayes' law. So we have probability of hidden variable given our observable equal to the exact opposite, literally the converse, where we just flip the order. So now we have probability of our observable given our hidden variable times unconditional probability of our hidden variable divide by the same thing summed over all possible values of our hidden variable, and we plug in the expressions that we got in our earlier steps of our recipe and get an answer. So to a certain extent, the Bayes' law recipe, you ask yourself that list of questions: what's the hidden variable, what's the observable, what's the likelihood model, etc. It kind of gives you a very straightforward, clear path for how to tackle even potentially complicated, challenging inference problems. Questions about how that recipe applied to Monty Hall? Okay.